In this video, we continue our discussion of applications of partial derivatives and their meanings in thermodynamic systems. We'll go back to just a quick review of some of the issues we discussed on the previous video, remembering that we're expressing internal energy as a function of volume and temperature, and we have two partial derivatives here. The first one with respect to temperature we recognize as being the constant volume heat capacity. The partial derivative with respect to volume we recognize as being internal pressure, which we talked about in the last video. Now we'll consider an isothermal process for which the temperature remains constant throughout. So therefore the quantity CV dt is equal to 0 simply because dt is equal to 0. That means that because that term is equal to 0 in our expression for changes in internal energy, that what remains is the term which very simply just has the internal pressure. You'll also recall from our last video that the internal pressure is equal to 0 because it's related to interactions, and we'll talk a little bit more about that in a few seconds. So since the internal pressure is equal to 0, that means that du is equal to 0 in this particular system. So let's talk a little bit more about why internal pressure is something that depends on interactions. If we look very closely at the definition of internal pressure, where it is equal to the partial derivative with respect to volume holding temperature constant. So here's the key. Temperature is held constant. It's an isothermal process. Why would internal energy change when we expand a gas, for example, when we increase its volume? If the temperature is being held constant, well, we know that the kinetic energy of the particles must remain constant, since the kinetic energy depends on temperature. So why else would the internal energy change? Well, the only way the internal energy changes if kinetic energy is constant would be if potential energy is changing. Well, potential energy is a measure and in fact is directly related to interactions. So if potential energy does change, that means there must be interactions between the molecules and the material that's undergoing the volume change. And therefore, for an ideal gas, since there are no interactions, there is no potential energy associated with those interactions, and that potential energy, because it is 0, will not change during an isothermal process. So again, the internal pressure only changes if there are interactions present within the substance. Let me reiterate. The internal energy is equal to non-zero only if there are interactions in the substance. Well, let's take a better look at this internal pressure so that we can deal with situations where we have a real gas or even liquids and solids to determine the effects of interactions on internal energy changes. So, first of all, there's an expression that we'll actually derive later in the semester. Well, there's something to look forward to. But right now, we're just going to start with this simple expression that says that du dv at constant T, which of course, again, is the internal pressure, is given by, on the right side of this equation, this expression which is related to the derivative pressure with respect to temperature at constant volume. All right. Well, let's apply this to an ideal gas. In the case of an ideal gas, we're going to use this expression to calculate the internal pressure. And we'll note, of course, that derivative of pressure, because P is equal to nRT over V, if we take the derivative of pressure with respect to temperature at constant volume, we get nR over V. All right. So we can do a substitution of that into the above equation. And when we do that, of course, we get this equation down below. All right. Well, we'll recognize this first term of this equation as being nRT over V, which is just the pressure. So we end up with pressure minus pressure, and that's equal to 0. which is exactly what we expect for an ideal gas. What we said earlier, because an ideal gas has no interactions, its internal pressure is equal to 0. Here we've derived it mathematically, which frankly I think is pretty cool. We've started out with some equations. We've derived an answer which is consistent with our qualitative expectation. We can explain this. We can actually understand why this is equal to 0 based on our understanding of interactions, and we can show it mathematically to be equal to 0. Pretty cool. Now let's take a look at what happens with the van der Waals gas, which has interactions, and how we can do a similar kind of derivation. So again, we start with the expression that we had on the previous slide for internal pressure, and we're going to go to the van der Waals equation given here, and we're going to take the derivative of that equation with respect to temperature. We'll note, of course, that when we take the derivative, we take the derivative of both terms, the first term and the second term. Now we'll note that the second term does not depend on temperature. And because it doesn't depend on temperature, the second term, when we take the derivative of that term, will go to 0. Again, noting that the second term, which is the attractive term in the van der Waals expression, being not dependent on temperature, when we take the derivative of that, it's like taking the derivative of the constant, so that goes to 0. And so when we end up with the derivative for the van der Waals gas, we just end up with that first term being non-zero. So we'll take that term and plug it into our expression, and we then have, in this situation, the first term. The second term, which is just P, well, we plug in the van der Waals equation for that, and what we find is that in this case, for van der Waals gas, we end up with the internal pressure being equal to the A times N over V squared, the attractive term of the potential. Now this again should make sense. For an ideal gas, of course, it's equal to 0 because there are no interactions. Van der Waals gas does have interactions, and we'll note that the internal pressure is then just equal to the negative of the attractive term on the in the van der Waals equation. Again, because there are interactions, we show that the internal pressure is not equal to 0 for the van der Waals gas. So there's a theoretical method for determining this internal pressure. We can also attempt to measure this experimentally. This goes back to the slide that we discussed in the first video in this series from Chapter 3. So I'm not going to go through the derivation again, but the end result here in this case is that the internal pressure, which is this expression here, is given by this negative mu sub j, where mu sub j is the Joule coefficient, times the heat capacity, the constant volume heat capacity. Constant volume heat capacity we can measure in the laboratory. The Joule coefficient we can also measure, and we talked about this in the previous video. The Joule coefficient shows the change in temperature with respect to changes in volume, assuming that internal energy is held constant. So if we can design an experiment on a process which has a process where internal energy is constant and measure temperature changes that accompany a volume change, then we can get the Joule coefficient, and if we can get the Joule coefficient, we can calculate the experimental value for the internal pressure. So that's what we'll set out to do. Now, it's called the Joule coefficient because James Joule did indeed design an experiment that was set out where he set out to measure this particular coefficient. So here is a basic design of Joule's experiment. What he did was he put in a water bath, which is a huge amount of water with a fairly large heat capacity, 2 bulbs connected through a stopcock. Okay. Now, on one side, inside A here, we have gas present. Okay, so there's gas inside A, but on side B the pressure is 0, meaning that we have no gas. In fact, we've got a vacuum. on this particular side. So the basic idea was, with these two bulbs connected through this closed stopcock immersed in this water bath, what Joule set out to do was open the stopcock and allow the gas A to expand into the region B, where we had a vacuum. So there we have a volume change. So that has a volume change associated with it because it's an expansion. Alright, so the question is then, is delta U equal to 0 for this particular process? Well, we've got this huge water bath which is insulated from the surroundings. So in this situation, since we have a system that's isolated from the surroundings, clearly Q is equal to 0 because it's isolated from the surroundings, and the gas is doing no work in the process because it's isolated from the surroundings. So in this case, Q is equal to 0, W is equal to 0. So if Q is equal to 0 and W is equal to 0, that means that delta U is equal to 0. So we do have a constant internal energy process. So how does this work then? Well, if we then measure the temperature change that occurs, so you'll notice we have a thermometer here immersed in this bath, so we'll measure the temperature change. We measure the temperature change that accompanies the volume change, and because the process does not change the internal energy, by measuring the temperature change and the volume change at constant internal energy, we get the Joule coefficient. And again, remember, if we get the Joule coefficient, we can calculate the internal pressure. So what did Joule find? He found that when he tried to measure the temperature change, that he got a value of 0, so delta T is equal to 0, and from that he concluded that the Joule coefficient was equal to 0, and therefore internal pressure was equal to 0. So what does that mean? Does it mean that the gas was behaving ideally? Well, no. The problem here is that because the water bath was so large and water has such a high heat capacity, that even though there was a temperature change in the process, it was actually too small for him to measure. So his equipment was not capable of measuring the temperature change associated with this, so ultimately it was an unsuccessful experiment. In the next video, we'll talk about additional experiments that have been done to make better determinations of internal pressure and the effects of interaction on the internal energy of a substance. Stay tuned.